In this video, we'll talk about conditional probability and we'll do a few examples of this. First of all, conditional probability means that you're assuming that one event has happened and you want the probability of another event after that. And the notation we use for this is P of B given A, and for the given we use a vertical line. This represents the probability of event B occurring after it is assumed that event A has already occurred. So this is read as B given A. The multiplication rule says the probability of A intersection B, which is the same as the probability of A and B, is equal to the probability of A times the probability of B given A. Most of the time we're going to use this rule in a different form, and that is to find a conditional probability. So if we rearrange that rule a little bit, we have the probability of B given A equals the probability of A intersection B divided by the probability of A. Now if A and B are independent events, in other words, one event doesn't affect the other, then P of B given A is going to be the same as the probability of B. Here's our first example. We have the same numbers from the survey that we used in the last video, and from these values we want to find the probability that a randomly selected person from this group is over 65, given that the person is female. So here's the notation. We want to find the probability that they're over 65, given that they're female. The first way we can do this, if we already have the numbers in a table, is that we can just look at the row of the table where our respondents are female, because those are the only ones that we're interested in. We already know the person is female, then we can just consider that as our complete data set. So we can look at this row right here, and then if we want to find the probability out of those values that a person from that group is over 65, we're going to take the number that we're over 65, which is 16, and divide by the total of this whole row, which is 39. So when we divide 16 by 39, we get 0.4103 or 41.03%. The second way to do this is by using that multiplication rule that we were talking about. So what that says is that the probability of the person being over 65, given that they're female, is the same as the probability of someone being over 65 and female divided by the probability of them being female. So that means we have to figure out both of those probabilities. So for over 65 and female, we're going to be looking again at this one cell in our table, which has 16. Now we want the probability of that out of this whole group, including the males. So we're going to divide the 16 by 80, which is the total of that whole table. That gives us 0.2. Then we also need the probability of female. Well, we know the total of the female row is 39, so we're going to divide 39 by 80 and get 0.4875. So to get our final answer, we divide the 0.2 by the 0.4875, and this way also we get 41.03%. Here's another example. What is the probability that a randomly selected person from this group is male, given that the person is not under 18? So we want to find the probability of male given not under 18. And notice that our event not under 18 is not one of our columns in the table. So we can think of it as a complement of the event under 18, which would mean it's everything except this column. Or we can think of it as a union of two mutually exclusive events, which would be 18 over 65 and over 65. So in other words, if we wanted to do that, we could look at these four cells in the table. Those are all the people out of this group that were not under 18. Our first method is that we're going to look at those 4 cells in the table, and the total for those 4 cells is 66. So the total for this is 66. And we're just looking at the males in that group. The ones in there that were male were this cell and this cell. So the number of respondents there is 31. So our probability is going to be 31 over 66, which gives us 46.97%. Our second method, again, is using the multiplication rule. So for this, we need to find the probability that someone is male and not under 18, and divide that by the probability that someone is not under 18. And again, for both of these, we're considering the probabilities as it relates to this whole table of values. Male and not under 18 would be these 2 cells that we already have circled up here, the 22 and the 9. So we want to add those 2 together, divide by the total from the whole table, which was 80, and that gives us 0.3875. Then to find the probability of not under 18, we need the total of all the people in the table that were not under 18. We already found that total was 66. So our probability for that is 66 divided by 80, which is 0.825. So for our answer, we divide the 0.3875 by the 0.825, and again we get 46.97%. Finally, our third example, a Morgan Stanley Consumer Research Survey sampled men and women and asked each whether they preferred to drink plain bottled water or a sports drink, such as Gatorade or Propel Fitness water. Suppose that the study included 240 men and 270 women, and that out of all of those, 350 reported they preferred plain bottled water. Of the group that preferred a sports drink, 100 were men and 60 were women. So we're going to define 4 events. M is the event the consumer is a man. W is the event the consumer is a woman. B is the event the consumer preferred plain bottled water. And S is the event the consumer preferred a sports drink. First of all, we want to find the probability of B. So B was our event that the consumer preferred plain bottled water. What we can do is just divide the number of sample points in our event B by the total number of sample points in the sample space. In other words, we're dividing the number of respondents that prefer plain bottled water by the total number of survey respondents. The number that preferred bottled water was up here, the 350. To get our total number of survey respondents, we had that there were 240 men and 270 women. So if we add those together, we get our total for the survey. So this actually comes out to be 510. So if we divide those 2, we get 0.68627. Now for our final answer, since it asked us to round to 3 decimals, then we're going to round that to 0.686. Next question, what is the probability of S? S was the event the consumer preferred a sports drink. That means we need to divide the number of respondents that prefer a sports drink by the total number of survey respondents. This one is pretty similar to the last one. We know that 350 out of our whole survey preferred plain bottled water, so the rest of them must have said that they preferred a sports drink. We could take our total in the survey, which was 510, and subtract the 350 to get our total that preferred a sports drink, and this actually comes out to be 160. So we're taking 160 and dividing it by our total again, which is 510, and that gives us 0.31373. Now we could have also done this if we had noticed that B and S are actually complementary events. Since there were only 2 choices in this survey, they either could say they preferred plain bottled water or they could say they preferred a sports drink. That means the events are complementary. Since we already had the probability of B was 0.686, the probability of S would just be 1 minus that. So we could have calculated our probability of S just by using the complement. Either way, when we round it to 3 decimals, we get 0.314. Okay, continuing with this example, now we're going to find a couple of conditional probabilities. So what are the probability of M given S and the probability of W given S? Remember that M was the event that the consumer is a man, and W is the event that the consumer was a woman. Here are our formulas from the multiplication rule for our conditional probabilities. So we already know P of S in both of these. We're going to need to find the probability of M intersection S and the probability of W intersection S in order to calculate these. The probability of M intersection S, to get that we need the number of respondents that were male and preferred a sports drink divided by the total number of survey responses. It told us that of those that preferred a sports drink, 100 were male, so we've got 100 divided by 510. So if we take that result and divide it by our probability of S that we had on the last page, we get 0.625. Now, one thing that's pretty important here is that notice in these we're not using the rounded values. Notice here we went out to 5 decimal places. The reason for that is that if we used our rounded values, even where we had rounded to 3 decimal places and then divided, we would have come up with not as accurate an answer here. It wouldn't be accurate all the way to 3 decimal places. However accurate you want your answer to be, you should have your intermediate results going out to at least 1 more decimal place than that. So if we want to take this out to 3 decimal places, we should have our intermediate results here going out to at least 4 decimal places in order to get the accuracy that we want. Now to find the probability of W given S, now we need the number of respondents that were female and preferred a sports drink divided by the total number of respondents. So again, they told us in the problem that of those that preferred a sports drink, 60 were female. So we're taking 60 dividing by 510 to get 0.11765. We're going to divide that by the probability of S, and again we've got 5 decimal places in each of these, and we divide, we get 0.375. Notice that P of M given S and P of W given S add up to 1. If we think about it, are those two events complementary? So in other words, if we already know that the respondent that we're looking at had said they preferred a sports drink, are the M and the S complementary? And the answer is yes, because again, if we were just looking at those that said they preferred a sports drink, there are only 2 choices for their gender, either male or female. Okay, so our final part of this problem is to look at the events S and W and determine whether they're independent. In other words, is preference for a sports drink independent of whether the consumer is a female? So what does it take to be independent? Well, if they are independent, then our conditional probability would have to be the same as the probability of an event alone. And the conditional probability we already calculated that has W and S in it was this one up here. If they are independent, then the probability of W given S would be the same as the probability of W. Well, we know our probability of W given S. The probability of W would be 270, since there were 270 women in the survey, divided by 510, which turns out to be 0.52941. Well, this is not anything even close to our probability of W given S, which was 0.375, so that means they're not independent. So in other words, it does matter whether the consumer is male or female as to their preference for a sports drink or plain bottled water.